So the first component we're going to talk about is the hydraulic pumps, and these are critical. They're going to convert mechanical energy to fluid pressure. And now I know I've mentioned that some of our pumps are AC motor driven. AC, they use their motor, but a motor is converting electrical energy to mechanical energy. You still then have a pump converting that mechanical rotation to pressure. And so, we can directly convert the mechanical rotation from the engine to pressure. We can convert electrical to mechanical energy using a motor and then convert that to pressure. But I've also talked about then you can use a hand pump to create pressure. There are the power transfer units take hydraulic energy, convert it to rotary motion, and then convert it back to hydraulic power. So, the pumps can get the energy they use to create that potential energy in the form of pressure several different ways. But for our purposes, what these are going to be, these variable displacement constant pressure pumps, are going to be a piston type pump. And this is where I've got, some animations here, and I've got some pumps a pump I can bring in to look at. That's where we'll do the kind of the show and tell next time. But these pumps are designed to create pressures over 1500 psi. And again, most of these systems are running at 3000 psi. Some of your aircraft nowadays are running upwards of 5 or 6000 psi. Occasionally, you'll still see a gear pump or a vane pump. But as you can see on the slide, these don't offer the pressures that the piston pumps are able to offer. And they're called an axial piston pump because you have a set of pistons spinning around the axis of the pump. So I've got some cutaway diagrams of them, and then we'll look at animations next time. So we should go to a piston type pump. It's kind of not the greatest drawing, but a black and white sketch. Has that gone over?
Yep.
Yes.
Okay. So we have a piston pump here, and the pump itself is driven mechanically on the right side. We have a shaft right here, and this is our input shaft. And that input shaft can be a spline shaft directly that goes onto the gearbox of an engine, or it can be connected to an electric motor. And that shaft is going to spin this area in the middle that's made up of a cylinder block and pistons. And as it spins that cylinder block, those pistons are attached on an angled plate right here. It's called a yoke, or you'll also hear it called a swash plate. And so because that's at an angle as it spins, as this cylinder block, which is kind of this piece here, as that rotates, it's gonna, at the bottom, these pistons are gonna get pushed in by that angled plate, by that angled yoke or swash plate. And when they rotate around to the top, in this case, they are going to get pulled out. They're going to get pulled back. So here the piston's been pulled back at the top. Here this piston's been pushed in. So fluid will get sucked in at the top, and then as that chamber and piston rotates around, it'll get pushed out at the bottom. And that's where we get our pressure from. That's the main core of the pump. Now the pump itself, these are not the greatest at being self-priming. So if they get air in them, they really don't do a good job of getting started. And so this version right here has actually got a second pump kind of attached. It's got an impeller or a centrifugal pump on it that's used to help prime the piston pump. So this shows an integral impeller. What's more common nowadays are reservoirs that supply bootstrap pressure. And that is our reservoir where the fluid is stored is going to be under pressure somewhere around 8 to 15 psi, which is enough to force fluid into the intake of the pump and prevent the pump from getting, becoming cavitated, getting basically air bubbles in it. Some of the other things you'll see here on this cutaway is that, there is this, so you have your inlet here. You have your outlet here, at the bottom. And there is a third outlet right here that's labeled cooling flow. And what happens is a small amount of the fluid, rather than going into the pump, a small amount of the fluid that comes in goes in and is around the outside and is in this area outside of the pistons. And that area is, that fluid that goes in there is what's going to provide lubrication for the pump. So the pump is self-lubricated using the same hydraulic fluid that it's going to pump. It's also going to carry away any heat that is generated by the pump. So it cools the pump. So you have, they call it cooling flow. It's cooling and lubrication flow. And it's known as case drain. And so any of these pumps, most hydraulic pumps on aircraft are going to have 3 points where they have a hose connected to them. They're going to have an inlet where the fluid flows in. They're going to have an outlet where it comes out under high pressure, 3,000 or so PSI. And they're going to have the second outlet that is your case drain cooling flow, which is a lower pressure. It's just enough to go into the return side. The last part on here is down at the bottom. This shows a depressurization valve. And what that does is when it's opened, it bypasses, or it basically closes off this blocking valve and prevents the flow of fluid out of the pump into the system. And so that's the way that, if you need to shut off the flow of fluid from the hydraulic pump into the system, and you can't shut an engine down, this would be a pump that's mounted on an engine. That blocking valve can be closed, and it prevents the fluid from going out to the system, effectively turning the pump off. Now the pump will still be spinning. It doesn't mean all flow will be blocked off. You'll still have that cooling flow and lubrication flow through the case drain taking place. You just won't have fluid going out to the hydraulic system. And the way these are constant pressure variable displacement, the key to this whole thing is this angled yoke or swash plate. And the angle of that swash plate sets how much fluid is pumped. So right now it's angled fairly far over. That means it's going to draw, a space that big. The yoke swash plate angle can be varied by this actuator piston down here. And if the pressure starts to get too high in the outlet, this piston will get pushed to the right, and that will move the swash plate to a more vertical orientation. And if it's more vertical, it'll reduce the stroke length of the individual pistons in there. And you can kind of, this cylinder block and pistons, it almost looks like a revolver type, if you're familiar with a revolver gun, like an Old West revolver gun, where you have those, the holes that are drilled through a block that rotates. And each one of those has a piston in it. So when that yoke and swash plate is more vertical, the piston stroke is reduced. And effectively the amount of volume of fluid that the pump is going to move is going to be reduced. But it can still produce the same amount of pressure. So in the videos that I have, we'll watch those. There's some cutaways and things like that show how that swash plate is able to move in order to adjust the volume of fluid being pumped by the pump. We'll look at a couple of these, what they look like when they're actual pumps. So the next slide should show an engine-driven pump. Let me know when it switches over. Yep. Okay. Anyone know what this is? Where have you seen this before? Does this look familiar to anyone? No, this right here. So this pump, this is on the JT9. This is an engine-driven pump. This is the one that's in the hangar. So if you want to get a close-up look at it, it's on the side of the JT9 that faces out towards the aircraft where the Cirrus are parked. But just a few things to point out. I've got it circled here. I'm going to go back. Let me go back a slide. Did the circle disappear?
Yes.
Yellow circle's gone. Okay. So you can see it's got 3 hoses to it. Here is our inlet coming in. It's labeled inlet. Here is our outlet that's sending pressure out to the aircraft. And here is our case drain over here. Here is that depressurization valve that's used to effectively shut the pump off. And down here at the bottom is where it's mounted to the accessory case of the engine in order to spin the pump. And the actual pump itself, the cylinder block, the pistons, the swash plate, those all live in this area right here. Here's another one that's not installed on an aircraft. Is it switched over?
Yep.
Should be on its side now. Pump on its side. Kim, did this load?
Yes.
Yep, okay. So again, similar components. Now we can see the spline shaft on the left that would connect to the accessory gearbox on the engine. We have our suction line, our inlet. We have our pressure line coming above it, and then we have a case drain line right over here. And then here's that depressurization solenoid to be able to shut the pump off. And the pump itself lives in this area. Okay. One other item that you can see on here that we couldn't see on the last one is if this pump were to fail, we don't want it to damage the engine or bog down the engine. You can see they've made the shaft thinner. There's an area where an O-ring can go, and then the shaft gets thinner down in here. That's so that the spline portion can shear off. So if the pump gets jammed and the engine wants to keep spinning, it can shear that off and break it off and allow the engine to continue to operate. So I'm going to leave off with that. The next time we come back, next time we talk about hydraulics, we'll look at AC electric motor driven pumps and look into some of the, then continue on with other components that are in the hydraulic systems.